This particular titration curve example comes from Test 2, Spring 2010. And the example is, draw a titration curve for titration of a strong acid HI with a weak base NaCH3COO. So what's in the flask will be the strong acid HI, and what's in the burette will be the weak base. Alright, so let's look at what the titration curve will look like. Alright, we'll have pH along that axis, and what's being added to the flask will be the weak base. So volume of NaCH3COO is what we're going to see there. Now it says titration of a strong acid with a weak base, so we're going to start out with a pH of about 1. We're going to draw our curve, and it's going to look something like this. And the pH will end up at the pH of the weak base, which is going to be a pH of about 9. That's what we're going to put there. Alright, so the next thing we want to do is go ahead and see if we have a buffer region present. And let's say we're going to use this as our acid, and I'll call this A, and we'll call this base B. So what's going to happen is that we will have our acid. We'll start out with, say, 4 of them. And the acid will react with the base. And it will form an anion for the acid, and we'll get the base here. Alright, so let's look at what's going to be present if we have 2 of these acids reacting with 2 of the weak bases. So what we'll have is we'll have 2 A's that didn't react, and then we'll have 2 acids that react with a weak base. So what we've got here is A, which is a strong acid, and B, which is a weak BH, which is a weak acid, and it's the weak conjugate acid of this weak base. So all we've got present here at this point would be strong acid and weak conjugate acid, and this is not going to constitute a buffer region, so this one will not have a buffer region. And again, I want you to go back to my mini lecture on whether a buffer region will occur to understand this point. Alright, so no buffer region in this one. Let's look at the actual reaction. It'll be HI plus NaCH3COO COO. Now we can figure out what's going to join together if we look at this as being H plus, and we can look upon this as being, split this into ions, this will be H plus, which will make that I minus, and then we've got the Na, which we know is going to be Na plus, and we've got this, which we know is going to be CH3COO minus. The reason we know that this whole thing is negative is because we know sodium is positive. Now we don't have the convenience of seeing an H plus and an OH minus, but what we can see here is that any of these that have positive and negative is what's going to join together. So the H plus will join with this one, and the Na plus will join with the I minus, and that will give us our final reaction. So we can look upon this as being HCH3CO or CH3COOH is in the more familiar form of it. plus NaI. So you could write either of these for the first part of that reaction. But just understand that since it's a double displacement process, the cation from one will react with the anion of the other, and the cation of the other one will react with the anion of the other one. And that's always the way the pattern's going to work out. And that's a good general pattern for you to follow when you're trying to figure out what the products are from these reactions. So this is what's going to be present at the equivalence point. When equal amounts of each of these react, we're going to get acetic acid and sodium iodide. Let's see if that matches what we would expect for the equivalence point. We know that we can get the equivalence point by averaging the starting and finishing positions of the pH, and that's going to be about 5. So we'd expect the equivalence point to be weakly acidic, and that's exactly what we get. We get acetic acid, which is a weak acid, and we'll have sodium iodide, which is not going to affect the pH at all. Alright, so that's what we've got for the equivalence point and the reaction, so everything seems to work out there. Alright, let's look at finishing up the problem. We've got an estimating starting pH. We're starting out the strong acid, so we're going to have a pH of 1. We're looking at the pH and ending pH. Well, it's a weak base, so it's going to be a pH of about 9. And the best indicator used, well, that would be the one that covers the equivalence point, which is at 5. So I would use this one as my indicator, brome cresol green.